Hello Math 3680 students. Let's begin Lesson 13, Two-Sample Inference. This topic corresponds to Chapter 9 of the textbook, and I'm not so sure whether I can complete Chapter 9 in a single week. Let me try, and if I can't, then there'll be some remainder that'll be carried over to either week 14 or maybe week 15, depending upon how things go. Okay, let's begin. First, let's consider the two-sample inference for two dependent samples. We can consider two completely dependent data and two completely independent data, and somewhere in between, two correlated data. We're going to consider correlated data, or bivariate data, or regression analysis, whatever you may call those kind of things, in probably week 14 or 15, depending upon how things go. Here, we're going to spend about 5 to 10 minutes on dependent data, and the rest of the class time will be spent on two independent data. Here's a checklist, by the way. You can go through these. Now, here's an example. Oh, excuse me, this is just a theory part. Here's an example of two-sample inference of two dependent data. Please stop the playback and read through first. So what do we have? We have 10 people with cholesterol level taken before a certain nutrition education class and after class. So we have before data here and after data here. And these are completely dependent because we're talking about the same person. For patient number one, before class 275, after class 265, we have moderate reduction in cholesterol level. And subject number 4, for example, apparently this class didn't work, 235 and increased to 240. But for some people it worked out pretty well, like number 7, 310 down to 235. Number 6, 290 to 220, things like these. Now, the key here is we can simply pair up all those data, pre-class and post-class, and simply take the difference. Like this, pre-class minus post-class, or the other way around, post-class minus pre-class. Either way, it will work out. And consequently, we just get a one-sample inference. We just have a sample of 10 people and all these cholesterol levels, and these are all coming from measurement, so we can assume that the cholesterol levels must be normally distributed, and we can do interval estimation, kind of like this. Find a 95% confidence interval of the mean amount of the reduction. You can expect a picture like this. Let's see. Take the average of all these, and it turns out 24.5, and that's the expected value that goes right in the middle. And then we have a t-curve, 95% here, 0.5% here, 2.5% there. And how do you do this t analysis? Look at the t-curve with the degree of freedom of n-1, so it's 9, and so on and so forth. Everybody can do one sample inference. Here's a solution, by the way. So that's how you do it. If we have two completely dependent data, we can simply pair them up and take the difference, and we just have a one sample inference. What if we do hypothesis testing? The same data set, And we can simply take the difference, and then we have one sample inference. And then, of course, you'll have to set up hypothesis accordingly. Null hypothesis, usually no difference, no improvement. And alternative hypothesis in this case is obviously the class made a difference toward better. So it helped reducing the cholesterol level. And you can test with appropriate significance level. Here we are taking the significance level of 1%. How do we do it? Well, we have this kind of picture. Let me see. Where's the picture? Yeah, okay. Here's a visualization. So we begin from 0. That's a null hypothesis. And we're looking for the critical value. And the critical value comes from one sample inference. T-curve with t-table with level of significance of 1%, and the degree of freedom is 9. You can work out and you can find out the critical value. Turns out to be 26.634. So 24.5, the observed mean difference, falls in the null region. So we reject the alternative hypothesis and accept the null hypothesis. Now, what if I take a little bit larger significance level? Just 5%. 5% to the right. So red region will have to be bigger. So this critical value will retreat a little bit. If you do it like that, it'll turn out that alternative hypothesis wins in this case. So we can say that this nutritional class did make some difference toward better, toward lowering the cholesterol level if you use the significance level of 5%. What if you do with 2%, for example? Yeah, still alternative. As for the change of all these, basically you're looking for the change of the t-score based upon your alpha value. And consequently, this value here, and of course this value will differ, and that'll change the critical value, and consequently the conclusion. The detail is left to the students. After all, everything is just one sample inference.